Hey everyone, welcome back. We're diving into something today that I think you're going to find seriously cool. We're talking about robots.
Robots.
Yeah, robots, but not the kind you might be picturing.
Okay, I'm intrigued.
These are absolutely tiny, like smaller than a millimeter. And get this, they can fold themselves into different shapes.
Wow, that's incredible. How is that even possible?
It's all about this technique called Kirigami.
Kirigami, like origami.
Yeah, exactly. It's similar to origami, but with a really important twist.
And what's that?
Instead of just folding, Kirigami uses strategic cuts in the material, so you get even more flexibility.
I see. So it's like you're giving the material more freedom to move and bend.
Exactly, and that's how they make these tiny robots move.
So how does it actually work with the robot? So imagine a sheet, like paper, but much more high-tech, made of these tiny little panels.
Hundreds of them, right.
Hundreds, even thousands maybe, all connected by these microscopic hinges. And when you hit those hinges with a tiny jolt of electricity,
They fold.
exactly, and unfold in very specific ways.
Wow, so it's like the sheet is coming to life, morphing from 2D to 3D.
That's a great way to put it. But how does something this incredibly small actually move? Like, does it have tiny legs or...
That's where things get really wild. At that size, the normal rules of physics kind of go out the window. We're talking about the microscopic world where everything behaves differently.
So, like, our usual ideas about movement don't really apply here.
Right. Early attempts tried to use friction to make these microbots move. But with so many contact points at such a tiny scale, it was way too hard to control.
So how did they get around that?
They took a page from Mother Nature's book.
What do you mean?
Think about how microorganisms move through fluids, like how bacteria swim.
Okay, I'm with you.
This robot, it actually changes its shape to manipulate the fluid around it, propelling itself forward.
So it's more like swimming than walking.
Precisely.
That's seriously impressive. Taking inspiration from, what, single-celled organisms?
It's amazing, right?
Totally. But I have a feeling this is bigger than just building one tiny swimming robot.
You're absolutely right. When we start understanding how things work differently at such a small scale,
Yeah.
it impacts, well, tons of different fields, like especially medicine and material science.
Right. You mentioned something called elastronics before. What is that exactly?
So Elastronics, it's this whole new type of material. They're super flexible, like elastomers, but they also have electronic capabilities built right in, so they can sense things in their environment, even respond to them.
Okay, I'm picturing like a material that's almost alive.
Kind of.
Yeah.
I mean, you could have a material that repairs itself when it's damaged,
So like self-healing.
self-healing. Or, picture this, a device that can change its shape or color to blend in, like perfect camouflage.
That sounds like something straight out of a movie.
It does, doesn't it?
Uh-huh.
And then there are medical applications. Imagine implants that adjust to the body over time or deliver medication super precisely.
Okay, that's huge. But how do these little robots actually fit into all of this?
Think of them like the tiny building blocks of this whole new type of material. You can assemble them in different ways, program them to react to certain things.
And you get,
You get materials with properties we've never seen before in nature.
instead of something static, it can adapt and change based on the environment or how it's programmed.
That's the idea.
Yeah.
It's about making materials that are dynamic, as responsive as nature itself.
So how far off are we from seeing this stuff in action? Self-healing phones, clothes that change color.
Hold on, not quite yet.
Oh, right.
There are still some hurdles, like finding a way to power these robots without needing external wires. That's a big one.
Makes sense. They have to be able to move freely, right?
Exactly.
Yeah.
And if we want to use them for things like targeted drug delivery, we have to figure out how to get them to work seamlessly inside the human body.
Yeah, that doesn't sound easy.
Not at all. The human body is incredibly complex. It's a tough environment to navigate, even for a microbot.
I guess for now, I'll just have to be extra careful with my phone. No stuffing it in my pocket with my keys.
Probably a good rule for all of us.
True, true. But seriously, it sounds like this research is really pushing the limits of what we thought was possible.
It really is. It reminds me of when people first started working with computers or the internet.
Oh, I see what you mean.
Back then,
Yeah.
who could have imagined how much those technologies would change everything?
It's kind of mind-blowing when you think about it that way. We started by talking about this teeny tiny robot that can fold itself up.
Yeah.
And now we're imagining materials that could completely revolutionize, like, I don't even know how many industries.
It just shows you how a discovery in one area
They can have ripple effects everywhere.
Exactly.
Well, this has been a fascinating deep dive. The potential of these microscopic robots, this whole future of elastronics, it's incredible.
It's exciting stuff.
It really is. Thank you so much for joining me today and for, walking us through all of this.
My pleasure.
And to everyone listening, I hope this has given you a lot to think about. What could be possible if we learn to build with these kinds of materials that are as dynamic and responsive as nature itself? Until next time, keep those questions coming.